Inside every CNC machine that leaves DMG Mori's production facility in the Iga region of Japan, there is a module tucked inside the electrical cabinet. It contains a GPS receiver and a gyroscopic acceleration sensor. Those two components have one job. If the machine is physically moved from its registered address without a cryptographic authorization code from the factory in Japan, the machine's control system locks out. The spindle stops. Restart requires a direct call to Nagoya. The engineers who built this system were not being paranoid. They were responding to documented evidence of what was already happening to their products once those products entered the world. On February 19, 2024, Vladimir Putin signed an executive decree transferring 100% ownership of DMG Mori's machine tool plant in Ulyanovsk, Russia, directly to the Russian state. By the time the decree was published, investigators had already placed 148 DMG Mori machines inside active Russian weapons facilities. 36 of them were running on the production floor at ODK Saturn, the manufacturer of engines for KH-101 cruise missiles. If you are wondering how a Japanese family, starting with nothing in a defeated nation, built the most precise machines on Earth and then had to design a system to stop the world from turning them into weapons, keep watching till the end. Before we get into it, if you are watching for the first time, this is Trade Archive. We cover the companies that built the physical world. Subscribe and leave a like if that is the kind of story you are here for. Mori Rinpei was born in 1921 in Susami Town, Wakayama Prefecture, on the southern tip of Japan's Kii Peninsula, a narrow stretch of Pacific coastline with no significant industrial history. His father had run a shell button manufacturing business, producing the small flat fasteners used across Japan's textile trade. That business failed. When Rinpei graduated from Wakayama Normal School in 1942 and was drafted into the Imperial Army, the family had nothing left. He came back from the war in 1946 to a Japan that had managed to lose even more than it had when he left. The Allied occupation had placed heavy industrial manufacturing under strict restriction. The factory districts of Osaka and Nagoya were rubble or sitting idle under supervision, designed to ensure they stayed that way. Raw materials were controlled. Credit was nearly non-existent. A 26-year-old demobilized schoolteacher from a failed family business in a Pacific coastal town with no manufacturing tradition was not, by any rational accounting, positioned to build something significant. He relocated to Yamato-Koriyama, a small inland city in Nara Prefecture, surrounded by rice paddies, ancient castle walls, and an economy anchored in goldfish breeding that dated to the Edo period. Not an obvious industrial destination, but it was inexpensive, accessible by rail, and it had a population of people who needed work and a post-war economy that had given them very few ways to find it. His brothers joined him. Shigeru, 4 years younger. Yukio, 11 years younger. In October 1948, the three of them founded Mori Seiki and began manufacturing textile machinery. Not clothing, not fabric. The looms and knitting frames that produced fabric. This distinction is easy to read past and worth stopping on. The Mori family had watched a consumer product business collapse beneath them. What the shell button trade taught Rinpei, specifically through its failure, was a lesson about where durable value actually sits inside a manufacturing economy. Consumer products go out of demand. The machines that make those products do not, as long as somewhere in the world something is still being made. That was the founding philosophy of Mori Seiki, and it never left. By 1958, the logic of staying in textiles had run its course. Japan's economic focus had shifted from post-war recovery to sustained industrial expansion. The automotive sector was scaling rapidly. Shipbuilding was operating at capacity. An industrial ecosystem was being built from the ground up across the country, and it needed precision-machined metal components in volumes that Japan's existing manufacturing infrastructure was not equipped to supply. Rinpei recognized the moment. In 1958, Mori Seiki abandoned textile machinery entirely and entered the machine tool market with high-speed precision lathes. They were a 10-year-old company with 47 employees and no machining history, entering a market that already included Okuma, Yamazaki, and Niigata Engineering, firms with decades of customer relationships and established production reputations. What the Mori brothers understood was the physics of what separated a lathe worth buying from one that was not. A lathe turns a workpiece against a cutting tool to remove material and shape it. The engineering required to do it accurately, in continuous production, at tolerances measured in microns, for thousands of operating hours without the machine's geometry drifting, is not simple at all. In a precision lathe, everything flows from three physical realities. The spindle must be preloaded and classified to P4, bearing specification, or better, to minimize runout under cutting load. The bed must carry enough mass to absorb vibration before it propagates through the structure and into the part geometry. And the guideways must make contact with such uniformity that an oil film, not metal against metal, actually supports the moving saddle and carriage under load. Mori Seiki built heavy, thick cast iron beds with deep internal ribbing, guideways finished by hand using a process called scraping, where a craftsman uses a hardened blade and, at the final stages, bare fingertips to feel and remove the high spots from a precision sliding surface, improving contact area and oil film retention in a way that no grinding machine can consistently replicate. The technique was a traditional practice in Japan's precision manufacturing culture, but most companies were abandoning it for faster mechanical finishing methods. Mori Seiki kept it, elevated it, and made it a company identity that has persisted to the present. The Iga Campus today maintains an active scraping program, a deliberate investment in an analog precision method inside a company that would become one of the most software-intensive manufacturers in the world. You hold a micron over 30 years with mass, surface contact, and oil film. In 1968, the company built its first numerically controlled lathes, machines guided by punched tape programs and early computer logic rather than a machinist's hands. NC machines could hold tolerances and repeat cutting sequences across an entire production shift without the cumulative variation that human operators inevitably introduce. In 1970, the IGA plant opened in Mie Prefecture, on land in a region historically renowned for a different kind of precision work. It was the birthplace and training ground of the ninja, a mountainous interior suited by tradition to focused, technically demanding craft, conducted away from outside observation. The facility gave Mori Seiki the production capacity its growth required. By 1976, the company held the top market share position for NC lathes in Japan. Not second. Not close. First. 28 years after Rinpei returned from the war to a city that made goldfish and rice, the Mori family had produced Japan's leading precision machine tool manufacturer. The company listed on the Osaka Securities Exchange second section in 1979, moved to the Tokyo Stock Exchange second section in 1981, and was promoted to the first sections of both exchanges in 1983. That same year, Mori Seiki USA Incorporated opened in the American market, following Mori Seiki GmbH, established in Germany the year before. Rinpei stepped down from the presidency in 1986, transferring leadership to Yukio. He died in 2005 at 83, having run the company for 38 consecutive years without losing market leadership. Shigeru died in 2007. Yukio died that same year. By then, the company had passed to Yukio's son. Masahiko Mori was born on September 16, 1961, in Nara, and grew up inside a family whose identity and the company's identity were effectively the same thing. He enrolled at Kyoto University's Department of Precision Engineering and graduated in 1985. His undergraduate thesis was titled In-Process Monitoring of Tool Wear by Acoustic Emission. He did not go directly into the family business. Instead, he took a position at Itochu Corporation in Osaka, one of Japan's largest general trading companies, and spent 8 years in the industrial machinery division, selling textile equipment and advanced composite materials to industrial customers. This was a sustained education in how purchasing decisions are made at the customer level, what service responsiveness and machine uptime mean to a manufacturer whose production schedule depends on the equipment not going down, and what a sales organization needs to do to close the kind of long-cycle industrial transaction that machine tools require. He returned to Mori Seiki in 1993, became a director in 1994, and was made president in June 1999 at 37 years old. What he brought back with him was a conviction that the machines were only as good as the system built around them, and that the system needed rebuilding from the physics level up. 3 years after taking the presidency, he enrolled at the University of Tokyo. His doctoral dissertation, completed in 2003, examined the business models of domestic and foreign production in the machine tool industry. Masahiko Mori was formally studying his own company as an academic subject while simultaneously running it. The approach was consistent with how he treated the business overall, as a system to be understood from first principles and rebuilt accordingly, not a legacy to be maintained by inertia. DCG stands for Driven at the Center of Gravity, and it addressed a problem that had existed in machine tool design since computer-controlled axes were first built. A single ball screw driving an axis from its edge does not pass its driving force through the center of mass of the moving component. That offset creates a twisting moment around that center, which shows up as vibration in the cutting zone. At moderate feed rates, the effect is containable. At the high feed rates demanded by aerospace material removal, it accumulates, degrades surface finish, and accelerates tool wear. Mori Seiki engineers developed a configuration using dual ball screws positioned so the net force acts directly through the center of gravity, eliminating the twisting moment at its source rather than compensating for it downstream. DCG entered production in 2003 on the NV 4000 DCG and NH 4000 DCG and became standard architecture across the product line. DDM, direct drive motor, removed the mechanical gearboxes and belt drives from the rotary and tilt axes of 5-axis machines. Belt drives introduce backlash. The driven component moves slightly before the drive corrects the error, building positional inaccuracy into every 5-axis trajectory the machine executes. Putting the motor rotor directly on the rotary axis removed the intermediary entirely and delivered zero backlash, high torque, high-speed positioning on the B-axis and C-axis that define simultaneous 5-axis contouring. For aerospace machining, where positional accuracy across all 5 simultaneous axes determines whether a finished component passes or fails final inspection, the difference between backlash and zero backlash is not a footnote. It is the yield. BMT, built-in motor turret, was designed for the turning center product line. On a conventional live tooling lathe, a belt or gear train drives the milling spindles inside the tool turret. The drive generates heat that conducts into the turret casting. The casting expands. The cutting geometry shifts. A machinist running a long unattended production job watches the dimensional output drift. BMT moved the motor inside the turret casting itself, isolating the heat source from the structural surfaces that determine where the cutting tool actually sits in space. The result was improved torque, improved thermal stability, and a machine that could run extended production jobs without accumulating the drift that belt-driven architecture produced over time. BMT debuted on the NL series in 2004. In 2010, Mori Seiki purchased the measuring equipment business of Sony Manufacturing Systems Corporation and consolidated it as a wholly owned subsidiary named Magnescale Company Limited. Sony's Magnescale technology used magnetic linear encoders to measure axis position. The conventional alternative, glass optical scales, perform accurately in clean environments. In a production machine running aggressive flood coolant, the mist, chips, and fluid contamination that build up inside an encoder housing degrade the optical signal over time in ways that are measurable and cumulative. Magnetic encoders are not affected by this contamination. For a machine requiring sub-micron positional feedback across hours of continuous cutting, the degradation of the sensing system is not an abstract concern. That failure mode makes the machine unreliable. The Magnescale acquisition resolved this by integrating contamination-immune feedback directly into the machine's control architecture. The MAPS conversational control interface, the company's own proprietary overlay, evolved over successive generations into the CELOS system, connecting individual machines into real-time factory networks and making production data accessible across an entire facility. Taken together, this engineering program produced a product line with a specific and consistent reputation inside the machinist community. Mori Seiki machines did not drift. You set up the job at the start of the shift and trusted the output at the end of it. The SL series slant bed turning centers, developed through the late 1970s and refined across the following 2 decades, became the reference standard for heavy-duty job shop turning. The 45-degree inclined bed design used gravity to move chips away from the cutting zone by default. Heavily ribbed cast iron castings, P4 class spindle bearings, preloaded for rigidity under interrupted cutting loads. What machinists who ran SL series machines consistently reported in trade press letters and shop floor conversations across 30 years was the ability to take interrupted cuts in hardened steel and hold the geometry. A lesser machine chatters under those loads and loses its dimensional accuracy in the process. SL machines absorbed them. Shops that bought an SL2 in the mid-1980s were often still running it on productive second-shift operations in 2005, not because a replacement was beyond their budget, but because the machine still performed. The MV40 Vertical Machining Center of the same era developed a parallel reputation: boxway construction, heavy castings, friction-damped guideways. Not the fastest machine in its class, the most dimensionally stable. A secondary market for used MV40s persisted for decades after production ended, with prices that reflected not sentiment but documented ongoing capability. A 30-year-old Mori Seiki Vertical Machining Center, maintained by people who understood what they had, held tolerances that entry-level modern production machines could not consistently replicate. The NL and NLX series succeeded the SL line in the mid-2000s and the 2010s, integrating BMT and an active thermal management system that circulated coolant through the machine castings themselves to suppress dimensional drift during extended production runs. The NLX 2500 became the benchmark flexible turning center for job shops and aerospace subcontractors across multiple continents. The NTX and NT mill turn platforms combined full turning capability with B-axis live milling on a single machine, allowing complex aerospace and medical components to be completed in one setup and eliminating the positional error introduced by transferring parts between separate machines. At the 5-axis tier, the DMU-50 brought simultaneous 5-axis capability to a footprint accessible for shops without the floor space or capital for full horizontal machining centers, with the Speedmaster spindle option reaching 20,000 RPM in high-speed configuration. The NHX 4000 horizontal machining center served the automotive production environment directly, delivering 1.2 G acceleration across all rapid axes and chip-to-chip times of 2.2 seconds, designed for a world where every second of non-cutting time in a high-volume transfer line is a revenue cost that compounds across a 3-shift production schedule. This was the product empire that 15 years of Masahiko Mori's engineering program had built. What came next was the part that does not appear in the product brochures. Gildemeister AG was founded on October 1, 1870, in Bielefeld, Germany, by a master locksmith named Friedrich Gildemeister. Over the following century, through multiple product generations and structural changes, it had evolved into Gildemeister, or DMG, Europe's dominant manufacturer of 5-axis vertical machining centers for aerospace, die and mold, and precision component production. Mori Seiki's engineering identity had been built around rigidity in turning and horizontal machining. DMG had been built around simultaneous 5-axis vertical milling. At the top of their respective specializations, the two companies were not really competing with each other. They were filling different halves of the same global market. In early 2009, navigating the aftermath of the global financial crisis, the two companies entered a capital and business alliance, each acquiring a 5% stake in the other and beginning joint product development and distribution. By October 2013, they presented a unified brand, DMG MORI. By 2015, Masahiko Mori had initiated the formal legal process to complete the consolidation through a domination and profit transfer agreement under German corporate law, which would bring both entities under a single corporate structure and end the decade of partial alliance. To execute the agreement required a supermajority shareholder vote at the German AG entity. Elliott Management, the activist hedge fund founded by Paul Singer in New York, had been quietly accumulating a significant stake in DMG MORI Aktiengesellschaft, which it disclosed in January 2015. By holding that stake, Elliott gave itself the power to block the shareholder vote the agreement required. The mechanism was straightforward. The Japanese parent had spent 6 years building toward a specific corporate outcome and needed those shares to complete it. Elliott had no particular interest in machine tools, and every interest in extracting a premium from a counterparty with a time-sensitive and specific need. The standoff resolved the way these standoffs resolve. DMG MORI acquired the blocking stake at a premium sufficient to make the exit worthwhile for Elliott. The DPTA was signed on June 2, 2016, and became effective on August 24 of that year. The specific premium paid was never disclosed. The merger was complete. The geopolitical dimension of the story had surfaced years before Russia made it undeniable. In 2009, the United States State Department cables, subsequently published by WikiLeaks, documented American concern about Iranian front companies procuring precision CNC machines through Taiwanese intermediaries. The cables named Ardalan Machineries, linked to Iran's Shahid Hemmet Industrial Group, the state entity responsible for liquid propellant ballistic missile development, as having sought Mori Seiki branded 5-axis machining centers produced by Taiwanese manufacturers. Faratech CNC Milling Services was identified in connection with efforts to source a CNC rotary table from Taiwan's Tanxing Accurate Industrial Company. The equipment referenced was Taiwanese produced under the Mori Seiki brand, not manufactured at the Japanese parent's own facilities. These were not front companies seeking generic CNC equipment. They were seeking Mori Seiki by name because the engineering reputation was precisely what their programs required, and they were willing to route procurement through multiple intermediaries across multiple countries to obtain it. The cables did not allege that Mori Seiki had knowingly exported to Iran. They documented that the company's engineering reputation had become a target for hostile weapons programs operating entirely outside the export controls the company could reach. This is the permanent condition of dual-use manufacturing. The same simultaneous 5-axis contouring capability that produces a titanium hip replacement produces the turbine disc of a ballistic missile guidance system. The machine does not know what it is making, and no engineering specification can distinguish one application from the other at the physics level. Export control frameworks work until they encounter a procurement network with sufficient resources and patience to find a way through them. Russia demonstrated what happens when that network is the state itself. In September 2015, DMG MORI opened the Ulyanovsk machine tool plant in Ulyanovsk, a city on the Volga River in central Russia. The facility covered 21,000 square meters, with a 3,300 square meter assembly hall and a designed production capacity of roughly 1,200 machines per year. At peak operation, it was generating 2.8 billion rubles in annual revenue. The business rationale was coherent and conventional. Local Russian assembly reduced import duties, shortened delivery lead times, and gave DMG MORI a deeper operational presence in a market with genuine manufacturing demand. Russia invaded Ukraine on February 24, 2022. On March 14, 2022, DMG MORI's supervisory and executive boards announced an immediate halt to all Russian sales, service, and production, including operations at the Ulyanovsk plant. But the machines already installed across Russia's industrial landscape were not going anywhere, and the people who had spent years running DMG MORI's Russian operations were not finished. Ukraine's Defense Intelligence Directorate, working alongside Ukrainian government investigators and journalists at DZIT and other European outlets, began systematically documenting the location and current application of DMG MORI machines across Russia's weapons production infrastructure. What they published across 2023 and into 2024 was specific. They found 148 DMG MORI machines operating inside active Russian weapons facilities. 36 of them were on the production floor at 000 UEC Saturn, which manufactures engines for KH-101 cruise missiles and Su-57 fighter aircraft. Additional machines were documented at the Kalashnikov concern at the Ulan-Ude aviation plant producing Mi-8 military transport helicopters, and at the Ijevsk Kupol facility, manufacturing Tor surface-to-air missile systems. On September 20, 2023, Ukraine's National Agency on Corruption Prevention formally added DMG MORI to its list of international war sponsors, citing documented deliveries of machine tool components by DMG MORI Rus to a subsidiary of UEC Saturn after the invasion had begun, with a Moscow arbitration court decision as part of its evidentiary basis. DMG MORI denied authorizing any post-invasion supply to Russian defense customers. But here is the detail that complicated the company's position. DMG MORI's own internal investigation found and disclosed that former employees of 3 Russian DMG MORI entities had sold 122 units of equipment without authorization from company management after the official halt was announced. Rustam Alyautdinov, formerly the sales director of DMG MORI Rus, had established a shell company named DM Technologies in the same Ulyanovsk industrial zone as the halted plant and had continued operating from within it, supplying machines and spare parts to customers that included entities in the Russian defense sector. The company acknowledged the 122 unauthorized sales, denied corporate-level involvement, and stated it had taken steps to address the breach. The investigators' documented findings and the company's stated position remain unreconciled. On February 19, 2024, Putin signed the decree. Russia's Federal Property Management Agency, Rosimущestvo, received 100% ownership of the Ulyanovsk machine tool plant by executive transfer. DMG MORI confirmed the expropriation in its own financial filings, recording a loss from discontinued operations of 91.9 million euros and noting the deconsolidation of the Russian entity. By the summer of 2024, the seized facility had rehired workers, entered a cooperation agreement with Rostec's Aviastar subsidiary on production, supporting the IL-76 military transport aircraft program, and resumed manufacturing under state management. By 2026, machines produced at the former DMG MORI plant had received official Russian domestic product certification under government decree, stripped of the German-Japanese branding entirely. The company that designed and built those machines was gone from the nameplate. The machines ran on. DMG MORI had begun equipping its machines with GPS-based relocation detection as a direct response to the dual-use exposure the Iranian cables had made visible and that Russia was making irreversible. A GPS receiver inside the machine's electrical cabinet tracks the registered installation address. A gyroscopic accelerometer detects physical displacement. If the sensors register an unauthorized relocation, the control locks out locally. The spindle stops, and reactivation requires a code from the factory in Japan. The company states the purpose plainly in its export control documentation, noting that the system exists to prevent military use through unauthorized transfer or post-bankruptcy redistribution. It is a reversible local lockout, not a remote kill switch, not a permanent deactivation. Whether a reversible local lockout is a meaningful deterrent against a state actor who has already seized the physical facility by presidential decree is a question the system's designers were not engineering against in 2014, but could not avoid thinking about in 2024. This is the story of Mori Seiki. If this is the kind of industrial history you want more of, subscribe to Trade Archive and leave a like. It tells the algorithm this video is worth reaching new viewers, which is the only way this channel grows. We'll see you in the next one.